Class 11th Chemistry, Unit 3, Classification of Elements and Periodicity in Properties. In this video, we will discuss about periodicity of valency or oxidation states, anomalous properties of second period elements, and periodic trends and chemical reactivity. First come to valency. What is valency? In the lower standard you discussed. Combining capacity of an element is called its valency. Valency of an element is determined by the number of valence electrons present in the outermost shell of its atom. For representative element means S block and P block elements. That is, elements belong to group 1, 2 and 13 to 18. Valency is equal to number of valence electrons, or valency is equal to 8 minus number of valence electrons. You can see these are the groups 1, 2, 13, 14, 15, 16, 17, 18. Okay. Number of valence electrons. This is 1, 2, 3, 4, 5, 6, 7, 8. Hence, valence is this is 1, 2, 3, 4 equal to number of valence electron. Now in this case, valence is either 3 and 5, 2 and 6, 1 and 7, 0 and 8. Either equal to number of valence electrons or 8 minus number of valence electrons. Now again you can see formula of hydrides and oxides. This is LiH, NaH, KH. This is CaH2 because valency of second group element is 2. That's why formula of hydrides of these element is CaH2. If we take the particular example calcium, this is for group 13 B2S6 ALS3, for group 14 CH4 SiH4 GeH4 SnH4, group 15 NH3 PH3 ASH3 SbH3, group 16 H2O, H2S, H2Se, H2Te, and group 17 HF, HCl, HBr, HI. The same way, oxide. First, oxides of the group 1 element. This is Li2O, Na2O, K2. Okay, valency of alkali metals is 1 and valency of oxygen is 2. That's why we can write formula in this way. For this second group element, MgO, CaO, SrO, BaO. 13 group elements B2O3, Al2O3, Ga2O3, In2O3. Group 14 elements CO2, SiO2, GeO2, SnO2, PbO2. Now in case of group 15 elements, they show valency of 3 and 5. That's why two type of oxides are there, N2O3, N2O5, P4O6, P4O10, AS2O3, AS2O5, SB2O3, SB2O5, Bi2O3. Group 16, this is SO3, SeO3, TeO3. And group 17, Cl2O7. Oxidation state. What is oxidation state? Oxidation state of an element in a particular compound can be defined as the charge acquired by its atom on the basis of electronegative consideration from other atoms in the molecule. This is oxidation state. Actually, this is the charge developed or charge present on the atom in a compound. Okay, consider some examples like OF2 and Na2O. If we compare their electronegativity, the order of electronegativity of the three elements involved in these compounds is F, O, Na. F most electronegative and Na is the least electronegative in these three elements. Each fluorine atom, electronic configuration is 2s2 2p5, shares one electron with oxygen in OF2 molecule. Now, being highest electronegative element, fluorine is given oxidation state -1. Okay. Oxygen 2s2 2p4 shares 2 electrons, one from each fluorine atom, and thereby exhibits oxidation state +2. Simply we can say in this the oxidation state of fluorine is -1 and this molecule is neutral. That's why oxidation state of oxygen will be +2. We can say oxygen is less electronegative compared to fluorine. That's why oxidation state of oxygen is in plus and oxidation state of fluorine is in minus. In Na2O, oxygen being more electronegative accepts 2 electrons, one from each of the 2 sodium atoms, and thus shows oxidation state -2. Remember, in case of OF2, oxidation state of oxygen is +2, while in case of Na2O, its oxidation state is -2. On the other hand, sodium 3s1 loses 1 electron to oxygen and is given oxidation state +1. Okay, there is one chapter, redox reaction. We will discuss about oxidation state in detail. There is one question. Using the periodic table, predict the formulas of compounds which might be formed by the following pairs of elements. To write the answer of this question, you must know the valency of these elements, like silicon and bromine. Okay, silicon, group 14 element, its valence is 4. Bromine, group 17, that is halogen family, its valence is 1. That's why its formula is SiBr4, SiBr4. Aluminium and sulfur, aluminium, group 13 element, valence is 3. Sulfur, group 16 element, valence is 2. That's why the formula is Al2S3. I think in lower classes you discussed, if you know the valency, how can you write the formula? That is aluminium, valence is 3, sulfur, valence is 2. If you interchange, okay, then we will get this Al2S3. Now, next question. Are the oxidation state and covalency of aluminium in AlClH2O5 plus same? Okay, that is covalency. Again, valency can also be defined by the number of electrons shared. Okay, that is, if number of electrons shared, that is equal to its covalency. Okay, if number of electrons are lost or gained, that is known as the electrovalency. Now, in this case, are the same? No, both are not same. Oxidation state of aluminium is +3 and the covalency is 6. Covalency can be found out by the bonds. This aluminium making the 6 bond, 1 with chlorine and 5 each with water molecule. That's why covalency is 6, and oxidation state is determined by considering the electronegativity of these species. Okay, and this will come +3. Anomalous properties of second period elements. First, we will discuss about diagonal relationship. Lithium and beryllium, the first elements of group 1 and group 2 respectively, exhibit some properties which are different from those of the other members of the respective group. In these anomalous properties, they resemble the second element of the following group. Thus, lithium shows similarities to magnesium and beryllium to aluminium in many of their properties. This type of diagonal similarity is commonly referred to as diagonal relationship in the periodic table. You can see this is group 1, this is group 2, and this is group 13. This lithium resemble in many properties with this magnesium, diagonally situated. This is beryllium resemble with aluminium in many properties, which is diagonally situated. So this is known as diagonal relationship. Now, what is the reason of this diagonal relationship? Diagonal relationship is due to the similarity in ionic size and or charge to radius ratio of the elements. Now, what are the properties which are different or similar? For example, lithium, unlike other alkali metals, and beryllium, unlike other alkaline earth metals, form compounds with predominantly covalent character. Compounds of lithium and beryllium are covalent, while other members of these groups predominantly form ionic compounds. The first element of each of the group, that is 13 to 17, that is boron to fluorine, also differs in many respects from the other members of their respective group. Now, what are the reasons for this anomalous behavior? Small size, large charge to radius ratio, high electronegativity of the elements, and absence of d orbitals. Now let us see. The first member of group has only 4 valency orbitals, 2s and 2p. Okay, because they belong to the second period element. That's why only second energy level is available. In the second energy level, that is one orbital from 2s and 3 orbital from 2p are available. Total number of 4 valency orbitals are available for bonding. Whereas the second member of the groups, that is third period element, have 9 valency orbitals, because from the third period d subshell started. That's why this is 1, 3 plus 5, 9 orbitals are available. Therefore, the maximum covalency of the first member of each group is 4. For example, BF4 minus, that is this 4, this the covalency is 4. Whereas the other members can expand their valency more than 4. For example, aluminium, AlF6 3 minus. The covalency of aluminium in this is 6. Furthermore, the first member of p block elements display greater ability to form p pi multiple bonds. Now again, what is the meaning of this p pi? In next chapter we will discuss about the different type of covalent bond, sigma bond and pi bond. Okay, this is one of the covalent bond, p pi. And the first member of p block elements can form this p pi bond, like carbon with carbon. Actually, when double bond or triple bond is there, one bond is sigma, always sigma, and another bond is pi bond. Okay, now in this way you can say one is sigma and one pi. When triple bond is there, this is one sigma and 2 pi bond is there. Okay, in the same way, like nitrogen double bond nitrogen, nitrogen triple bond nitrogen, and this double bond and triple bond collectively known as multiple bonds. Okay, and they can also form these multiple bonds with other second period elements. For example, carbon double bond oxygen, carbon double bond nitrogen, carbon double bond nitrogen, triple bond nitrogen, nitrogen double bond oxygen, compared to subsequent members of the same group. Now, periodic trends and chemical reactivity. The ionization enthalpy of the extreme left element in a period is the least, and the electron gain enthalpy of the element on the extreme right is the highest, except noble gases, which we have already discussed in the previous videos. This results into high chemical reactivity at the two extremes and the lowest in the center. Thus, the maximum chemical reactivity at the extreme left, that is among alkali metals, is exhibited by the loss of electron, leading to the formation of a cation, and at the extreme right, among the halogens, shown by gain of electron forming an anion. Reactivity of alkali metals increases down the group because of decrease in ionization enthalpy, and reactivity of halogens decreases down the group because electron gain enthalpy becomes less negative, and electron negativity also decreases down the group. Same way we can say alkali metals and halogens both are most reactive elements. But in case of alkali metals, reactivity increases down the group, while in case of halogens, reactivity decreases down the group. Now we can say alkali metals have tendency to lose the electron and show reactivity. That's why if ionization enthalpy is less, reactivity will be more. While halogens show the reactivity by accepting the electrons. That's why if electron gain enthalpy is more negative or electron negativity is more, then reactivity will be more. That's why this is the trend followed by alkali metals and halogens. Now, metallic character of an element which is the highest at the extremely left, okay, extremely left, that is alkali metals and alkaline earth metals, decreases, and the non-metallic character increases while moving from left to right across the period. This we also discussed. The chemical reactivity of an element can be best shown by its reaction with oxygen and halogens. And in this, we are taking the reaction with oxygen. Elements on two extremes of a period easily combine with oxygen to form oxides. The normal oxide formed by the element on extreme left is most basic. For example, sodium oxide Na2O. Whereas that formed by the element on extreme right is the most acidic, like Cl2O7. Oxides of elements in the center are amphoteric, like Al2O3, As2O3. I think you are familiar with this term amphoteric. Show the properties of acid as well as base. Or neutral, for example, CO, NO, and 2O. Amphoteric oxides behaves as acidic with bases and as basic with acids, whereas neutral oxides have no acidic or basic properties. Now, this is one question. Show by a chemical reaction with water that Na2O is a basic oxide and Cl2O7 is an acidic oxide. Answer is Na2O with water form a strong base, whereas Cl2O7 with water forms strong acid. This is the reaction. Na2O when react with the H2O, it forms NaOH, which is base. Cl2O7 when react with the H2O, it forms HClO4, perchloric acid. This is acidic in nature. Their basic or acidic nature can be qualitatively tested with litmus paper. Okay, student. Thank you. Subscribe my channel to get the new videos from next chapter.